Welcome to Artificial Intelligence for All, a forward-thinking initiative from a Princeton University startup, Qubits.ai. I am Professor Andy Gunawardena. It is hard to explain how neural networks compute complex functions. So, I want to explain this by showing the computation of a simple function. I will also demonstrate that the same neural network can be used to compute different functions by changing the weights. Unlike traditional programs, where we write an algorithm, neural networks learn from data. We feed them the data and the output, and the network learns the algorithm. Deep learning is really important when we have to learn a complex algorithm that we don't know how to program. So what is a neural network? Imagine each neuron as a tiny decision maker, the building blocks of our network. These neurons are organized into layers: an input layer, intermediate layers, and an output layer. Connections between neurons have weights that determine their influence. Positive weights mean more influence, while negative weights mean less. Each neuron uses an activation function to decide whether to fire or stay quiet. During training, the network learns by adjusting these weights and biases based on many examples, honing its decision-making skills. This allows neural networks to process complex data and recognize patterns, just like our brains do. Neural networks are fascinating yet complex systems, often hard to explain due to their intricate structure. They consist of thousands to millions of parameters, known as weights and biases, which adjust to perform tasks like recognizing images. Each layer of the network transforms data, often in abstract or unintuitive ways, distributing learned patterns across many neurons. This makes understanding their function challenging. Activation functions, such as sigmoid, introduce nonlinearity, enhancing the model's capability but also adding to its opacity. In essence, neural networks are powerful tools, but their inner workings can be quite enigmatic. A good way to understand neural network layers is to imagine providing it with an input, an image. It can go through many layers, identifying complex features of the image and eventually trying to recognize the object. The more layers you have, the more features you can understand. In the image, we show how the network may recognize various features of an image and guess what the image could be. Now let us build a simple neural network to compute the logical AND function. This exercise uses two binary inputs and produces one binary output, either 0 or 1. While computing an AND function might seem straightforward, and we don't actually need a neural network for this task, it serves as an excellent introduction to how neural networks operate. Through this basic example, you'll grasp the fundamental concepts of neural network architecture, including how inputs are processed to yield an output. Imagine a neural network with just one neuron, trained using only 4 input sets. Here's how it works. We assign weights to the inputs, with theta 0 set to -20, and both theta 1 and theta 2 set to 10. These weights help determine the neuron's output. For an AND function, the output is 1 only when both x1 and x2 inputs are 1. So, in our example, if both x1 and x2 are 1, the neuron fires, producing an output of 1. In all other cases, it outputs 0. We will compute this table to see the values of function output that is shown by the h theta x column. Now let's talk about applying the activation function, specifically the sigmoid function. The sigmoid function is crucial because it helps us transform the raw output of a neuron into a probability-like value between 0 and 1. This is especially useful in binary classification tasks where we want to determine if an input belongs to one class or another. By squeezing the output into this range, sigmoid effectively enables the network to learn complex nonlinear patterns. So after applying the activation function, we received outputs between 0 and 1. But we need to decide if the output is exactly 0 or 1, which is what we need. So we decide if the value is greater than 0.5, then it is 1, and otherwise it is 0. With this, we have shown the fourth column. That is exactly what we need the output to be. So you might ask, are the weights we selected special? The answer is no. We can choose many different weights to compute the A&D function, but not random. Those weights must be able to compute the function as shown by the process. Let's do some exercises now. Find a different set of weights to compute and function. Use the same network, but find some other set of weights to compute or function, and do the same for not function. We will show these calculations in the next video. In this video, we observed how a neural network computes a simple function. While the tasks we tackled, like AND, OR, and NOT, are straightforward and don't require neural networks, they set the stage for understanding more complex operations. We manually adjusted weights for a single neuron with one layer to mimic these functions. However, as networks grow with more layers, manual tuning becomes impractical. That's where the power of deep learning shines. Neural networks excel at handling complex functions and vast data sets, enabling them to perform tasks like image recognition, which are beyond traditional algorithms. So, while today's examples were basic, they illustrate the explainable principles of deep learning.